All right, so yeah, thanks again for the invitation, and thank you all for being here and for yeah coming to follow this sorry this talk. Uh, I'm speaking about a class of uh, generalized convex functions, and my talk will be sort of a survey over this class of functions. More precisely, I will speak about the results, so the properties of these functions and the results involving them, which were discovered until the beginning of the year, roughly speaking. In the meantime, there were also other results, other properties, but yeah, at some point one needs to stop and consider what's been done up to that point. Uh, the results of to which I am part of were also obtained with colleagues from Chile, Felipe Lara, Raul Macaviaca, and Vietnam. Or I mean, he's in France, but his Vietnamese Hun Nhan Nguyen. All right, so I'll start directly with the definition. What are these strongly quasi-convex functions? You might remember from economics, for instance, the class of quasi-convex functions, which are functions fulfilling this property without the blue part. H at the convex combination is less than equal the maximum of H at two points, which basically build this segment. And quasi-convex functions are sort of or a class of general convex functions. More precisely, the definition of a convex function, I guess it's known to everyone here. And the quasi-convex functions are an extension in the sense that they have a property, or they are defined by means of a property of the convex functions, more precisely that the sublevel sets of convex functions are convex. And they're used in economics. There are loss functions. They are defined. Yeah, there are loss functions which are quasi-convex or quasi-concave, which is basically binary quasi-convex, and utility functions as well. From convex functions, a special class are the so-called strongly convex functions, which are defined as you can see here. Their main advantage is that they have exactly one minimizer, and starting from quasi-convex functions, one can define similarly strongly quasi-convex functions. So basically, from the standard definition of quasi-convex functions, we withdraw exactly the term which is withdrawn in the which is subtracted, sorry, in the convex case to get strongly convex functions. And this definition has been introduced by Polyak in 1966. So it's not something we came up with or introduced just to have some fun. It has a history. Among the way, you'll see some citations. Nesterov, for instance, also worked with it. And yeah, there are, as I said, a number of papers dealing with with this class of functions. But first of all, let's place it in a context. Basically, strongly convex are strongly quasi-convex, vice versa doesn't always happen. And moreover, there are examples showing that the convex functions and the strongly quasi-convex ones are two classes which intersect each other but don't overlap. So none of them is included in the other. More precisely, norms are strongly quasi-convex, but not strongly convex. So first, a counterexample between these two. So these are included here, but not vice versa. And regarding strongly quasi-convex and convex, square root of the norm, for instance, is strongly quasi-convex on any bounded set, but not convex. And any constant function is convex, but not strongly quasi-convex. So basically these two classes, again, convex and strongly quasi-convex, they intersect each other. And we have a bit later some results exported, if you want, from convex to strongly quasi-convex functions, for instance, proximal type methods. However, not everything can be extended from convex to strongly quasi-convex. For instance, the sum of two strongly quasi-convex is not strongly quasi-convex. But this is expected since the same happens also for quasi-convex without strongly functions. And here, maybe it's also worth mentioning that both these properties, convexity, strong convexity, convex, I mean, all these properties can be considered on a set, which is a subset of the domain of the considered function. The domain is the set of the points where the function is not plus infinity. And yeah, that's why we have these examples on bounded convex sets and so on. Next, we'll present some properties of this class of functions. The composition with a linear operator is always so stays within the class, is always strongly quasi-convex. Also, the maximum of finitely many such functions stays in the class. These properties are also used or useful for quasi-convex functions. Then an interesting property regarding boundedness. Such a function cannot be bounded from above on an unbounded set. Such a property is a bit different than the standard properties of quasi-convex functions. So the strong part in these functions allows them to, or forces them to go to plus infinity on unbounded sets. These properties and also the others which follow here were determined by Jovanovic in the 90s. So you can see the interests on this type of functions was there always, even though it wasn't, let's say, in the mainstream. So not lots of people worked on them, but still they were considered and they were analyzed. An interesting property is this one, which extends a similar property known for quasi-convex functions, which are quadratic if and only if they are convex. For a solid convex cone, solid means its interior is non-empty. A function is quadratic a quadratic function is strongly convex if and only if it is strongly quasi-convex. So in this case, a property already known for more than a few decades was extended by Jovanovic, as you can see, to the strongly quasi-convex functions, more precisely their coincidence with the strongly convex on such a setting. So again, they have to be quadratic and defined on a solid convex cone. And one more property is this one, which moves between spaces, the property of strong convexity. More precisely, if we have a function which is defined on Rn or on a subset of Rn, it is strongly quasi-convex if and only if this function constructed by means of the initial function, but mapping from R to R is strongly quasi-convex on this interval. So sometimes it's difficult to work with functions defined on higher dimensional spaces. And such a property allows decreasing the dimension and focusing on really simple functions defined in R with values in on functions defined in R with values in R as well. All these upper indices, again, it doesn't mean k to the power 5. All these things are basically references or citations. Further, there are many other properties of these functions. As I said, we try to gather here in this presentation all the important ones which were obtained in the first almost 60 years of existence of these functions. And for instance, a strongly Quasiconvex functions is too supercoercive. You find here the definition of this notion because there are different types of coercivity. And now we come to some properties which are useful in algorithms. A proper strongly Quasiconvex function has at most one minimizer on a convex set. This means, of course, that we are dealing, this hints towards the fact that we might be dealing with minimizers in this case, and not with stationary or critical points as one usually has in case of non-convex functions. And the next property gives us even a more precise idea about this. If we add the lower semi-continuity to this proper strongly quasi-convex function, one gets exactly one minimizer on a closed convex set. So this was a hint to try to extend. So for us, it was a hint to try to extend the proximal method towards minimizing such functions, and to see if it delivers a stationary point, like again for quasi-convex functions and other classes of non-convex functions, or it delivers exactly the minimizer, the one minimizer of such functions. And surprisingly or not, the proximal method delivers or finds exactly this minimizer. Then, since I spoke about the proximal method, there are two properties involving the the proximity mapping. First of all, if our function is LSE and strongly quasi-convex, then its proximity operator on a set K, but this set can be the whole space, so it's we put it here more general, so the more general property, but again, it can be just the proximity operator of the function, is non-empty. It's not necessarily a singleton, but at least it's a non-empty set. And that's a useful property because, of course, in algorithms, no one wants to have the next step empty. I mean, the next iterate non-existing. Again, it's not singleton, so the proximal method would be in this case, like it's usually in the non-convex case, the next iterate belongs to the proximity mapping image, but so it's not equal to it like in the convex case, but on the other hand, it's again very important that it's non-empty, so we can iterate more and more. And also the minimizer of a proper LSE strongly quasi-convex function is nothing but the set. I mean, it has exactly one minimizer, and this minimizer is exactly the fixed point of its proximity operator. So something we know in the convex case, and it happens as well in the strong quasi-convex case as well. So you can see here again some of the properties of the of convex functions which can be extended to this class of strongly quasi-convex or properties from the strong convex. This minimize existence of exactly one minimizer on a closed convex set. Further properties, some technical ones. For instance, we have this descent property on a convex set, a strongly quasi-convex function, which has exactly one minimizer. Again, we saw this before. Presents this descent property. So h at some random point x in the set minus h at its minimizer, so the minimal value of h is greater or equal than such a quantity, which of course is useful in the convergence of algorithms. And another property which turns out to be a bit surprising, we have here an equivalence between several statements. Basically, a function is convex if and only if it plus quadratic term is quasi-convex or strongly convex or even strongly quasi-convex. So the first three equivalences were known before 2022. The fourth one was shown by my co-author Felipe Lara. And it's a bit surprising, but it works. And basically, you see that a function like this is quasi-convex if and only if it's strongly quasi-convex. So we have a property which mimics the one in the convex case, and also it connects to that property. So all these four statements are equivalent. Also, while my presentation is in Rn, always the function is defined on Rn and so on. Some properties can be extended for Hilbert spaces as well. We actually have a paper where we extended such properties. It will be not it's not published yet, but many of these properties, again, especially those involving only algebraic features, can be extended to such spaces and probably even to Banach or so. On the next slide, you see a new subdifferential. I know there are in the literature maybe at least 30 notions of generalized differentials, starting with the classical ones, Clark, Mordukowicz, or limiting if you want, Frechet, and so on. And all of them have some classes of functions on which they work nicely. The Clark one has the local Lipschitz and so on. And this strong subdifferential was introduced by Afghani and Lara, and they noticed that it is useful for dealing with strongly quasi-convex functions. Now, of course, you don't need to remember or to memorize these complicated formulas and so on. The takeaway message, if you want, or idea from this slide would be that there is a subdifferential notion which is non-empty. I mean, this differential is non-empty always for strongly quasi-convex functions. And it has some properties which will follow next. There's also a subgradient method for using it for strongly quasi-convex functions. However, there's also a, let's say, not so fortunate thing is that it is not easy to compute. Like many of the non-convex subdifferentials. But again, it's important to start something and then at some point maybe somebody will have a brilliant idea on how to compute this thing or how to develop from it a different notion which has better calculus on determination properties. Sorry, I went the wrong direction. And if we speak about strongly quasi-convex functions which are differentiable, so C1, one has this equivalence, which again mimics the characterization by means of gradients of convex or strongly convex functions. It's an if and only if statement, and it was determined or first published in 1978 by Vladimirov, Nesterov, and Chekhanov. Nesterov is indeed the Nesterov we all know. And the gradient of such a function, strongly quasi-convex, and C1, belongs actually to the subdifferential presented on the previous slide. So that subdifferential has this legitimacy that it contains the gradient in case it exists. However, unlike the convex one, we don't have here that the subdifferential contains exactly the gradient, it just includes it. So again, it's not a perfect tool, this new subdifferential, but at least it is useful in a certain sense. Moreover, a descent property, which is something called, so used to be called Leasiewicz, and in the meantime, following a talk by Boris Mordukovich this year, where I was also present, he proposed the name of Polyak-Leasiewicz Kurdyka property for such a property, because it combines several ideas from Polyak and also the Kurdyka-Leasiewicz property, which is very popular these days. So basically, such a property holds also for strongly quasi-convex functions, which are C1 with Lipschitz continuous gradients. So again, a hint toward proximal methods, algorithms, convergence rates, and so on. They can be obtained also in the strong quasi-convex case. Okay, I spoke for 20 minutes about properties and so on. Now let's see some examples, and you'll have 2 slides of examples of such functions, besides the ones presented after the definition. You can see here that these examples come from different areas, if you want, different classes of functions, even fractions and so on. Some of them are simple, for instance, such a function mapping the absolute value plus a shifting is convex and strongly quasi-convex, but not strongly convex. Some of them don't look convex at all, minus t square minus t. It can be seen as it's a concave function, or you want a DC function because it's the difference between this convex and this convex function. And it's also strongly quasi-convex, at least on 0, 1. Such a function minus exponential, constant minus exponential to minus x to the power 2 is strongly quasi-convex on this ball. Maybe an observation which could be useful is that some of these examples, or most of them, are given only or have the property of strong quasi-convexity on intervals, which means that this property has or is useful on a local level many times or mostly. And this could be useful maybe in other areas about which you don't know. So if anybody in the audience has another example of or a potential example of such a function, even again on some intervals, on some subset, please feel free to share because we aim to extend the usability of these functions and to gather or to collect as many properties and examples as possible. Uh, the next example, as you can see, is a trigonometric one plus a polynomial or plus a quadratic. Then such a perspective function is also strongly quasi-convex on an interval. Even the fourth root of a quadratic function is strongly quasi-convex, even though it's not convex. And if you remember from the first slides, from after the example, after the definition, we had the square root of a norm. Basically, not only the square root, but any power between 0 and 1 of a norm, in particular of the Euclidean norm, is strongly quasi-convex on a non-empty bounded and convex sets. Actually, this property was shown by Nicolas Hadjisavas. I forgot to put his name here as a citation. And on the second slide, you see the other examples I mentioned. They are fractions or ratios. More precisely, you might remember that if a function is convex, h is convex, g is uh, then concave, then h over g is quasi-convex. And starting from it, it was shown by actually by Felipe Lara and his Vietnamese co-authors that if we have h strongly convex, then h over g is strongly quasi-convex on the set K under three possible additional hypotheses. So if G is affine or G is concave and H is non-negative, or vice versa, G is convex and H non-positive. And this has as a special case such functions, quadratic divided by quadratic. If some things happen, so if this matrix is negative definite and the numerator is non-negative and so on. And this class of functions or these types of functions are useful also in finance and economics. So we expect yeah, maybe that in the near future, other or yeah, the other colleagues from these areas maybe start using or start acknowledging the existence of this class of functions and start using them or exploiting them, of course, if it fits their needs. And now we move toward optimization problems involving such functions, strongly quasi-convex. We minimize or we consider the problem minimizing such a function over an affine subspace. Affine subspace, we'll see a bit later why affine subspace is. Of course, K can be the whole set, the whole space, or it also can be a closed convex set, in which case some things in the algorithms have to be slightly changed in the algorithms for minimizing this. So again, the next slides are devoted to minimizing such functions, strongly quasi-convex. More precisely to giving algorithms for minimizing them. And the first one is something we produced. So I did it with my Chilean colleagues, Felipe and Raul. It is a relaxed inertial proximal point method for minimizing such functions. Inertial, because you have here an inertial step where the next iterate depends on the previous two iterates. Relaxation, because you have to hear this relaxation step. And proximal, because you have a proximal step. So, I mean, the standard sequence is xk, but it uses yk, tk to iterate. And we have here this proximal step. In this proximal step, as I said, we need to have that the next iterate belongs to the proximity mapping and is not equal to it, like in the convex case. So that's a bit of a disadvantage. On the other hand, this is always non-empty, and these two steps can always be made. So this algorithm is well defined. And I said that we need k to be affine because of the way this y is defined, this inertial step. And then in order to keep the feasibility, we need y to be, we need this construction to be in the set k. However, this can be avoided if one has the set k to be just closed convex. Then small changes in the algorithm can make it still stay well defined and usable. In case we remove the inertial step, so we take the alphas to be 0 and also the rows to be 0 here, then one gets the proximal point method, the standard proximal point method for minimizing such a strongly quasi-convex function. However, again, the difference to the convex case is the fact that the next iterate belongs to the set of to the proximity mapping, so the image set, and is not equal like in the convex case. So it's a small place to pry, I would say, in order to have the method extended here as well. As I said, the set K can be taken closed convex, in which case there are here three different ways of choosing or of modifying the algorithm. First of them would be to take here instead of yk, xk, so we use yk only here, not only here, not also here. Actually, the property of the algorithm is the properties are the same roughly, so the same class of convergence and so on. Nothing changes much. Also, one can use k. So one can use the algorithm for k closed convex instead of affine by taking a projection in the last step. So here, instead of leaving this, just project everything on k, or removing the inertial steps. So removing this, just taking this and this, one gets an algorithm for minimizing a strongly quasi-convex function over a closed convex set. Worth mentioning is that so we introduced this algorithm in 2022, and in the convex case, it was introduced in 2020 by Atouche and Cabot. So it's not something very old, very strange, quite recent, and it was based on dynamical systems actually. So also here another comment is that my co-authors extended this algorithm also for Bregman distances. So this way of extending proximal method in the convex case can be generalized also for strongly quasi-convex functions. Regarding the convergence, we have here some standard assumptions on the parameters involved. In particular, we take these alphas to be non-decreasing, again, more or less standard. And one gets here a technical result or technical convergence, so the distance between the points in this set and the xk's and so on is mapping exists, so the limit of this distance exists. And if we also impose another condition on the ck's play a role here, so they're the parameters of the proximity step, the proximal step, then xk converges to the minimizer of h, and h of xk converges to the minimal value of h. So as you can see, again, what I said before, in this case of the strongly quasi-convex functions, different to other classes of non-convex functions, we actually get convergence to the minimizer, like in the convex case. And this is a unique feature. As far as we know, there are no other classes of non-convex functions for which this happens. And this property again is something, or this property of the proximal method, or this property shows that the proximal method is useful also beyond convexity, actually, not just as a, let's say, academic adaptation, but really as a useful tool. There are also some properties regarding convergence rates. You can see them here. Yeah, a bit technical, I agree. So we'll go back to the next slide, where I'm presenting the subgradient method by Felipe and Raul and one of their students. The subgradient method determines zeros to the Strong's differential you've seen before. Again, it has a complicated structure. You don't have to memorize the way it's defined. But basically, it's this projected subgradient method works like in the convex case. If we find the zeros, the differential is stop. Otherwise, we take a subgradient of this type, project on K, and iterate. So the method is like in the convex case, quite simple. And convergence works under standard assumptions. Uh, one would say, yeah, these are a bit complicated assumptions, but they are mostly standard and also involve only the parameters. So they are not properties or hypotheses which are very heavy and involve, I don't know, some strange theory and so on. And again, the convergence goes to the minimizer of the function. H of xk converges to the minimum value of h. And if we had convexity, we even get at the limit of, sorry, if we had continuity, the limit of h of xk goes to h of x bar, to this minimal value. So again, the same advantage I mentioned before. Of course, in this subgradient method, it's a question how to determine the subdifferential. But again, I think that our role is to expand knowledge, and then somebody else might come and find a way to determine a set or a step or something like that. So it's important to push and push forward. And again, we have a theoretical method here, which might be useful at some point later, maybe. And on the next slides, we switch back, if you want, to differentiable strongly Quasiconvex functions. If H is C1, and we are over the whole space, then we have such gradient methods, gradient type methods, first order, and then will be also a bit more involved, heavy ball and so on. The difference between the standard gradient method and this one is that we also have some additional terms in some cases. As you can see, these results are quite recent by Rouhani, Raini, Piranfar, like 5 years or 4 years ago, and my co-authors and Fantu Wong last year. And they got quite nice results for the convergence of the gradient method under Lipschitz continuity of the gradient. One gets convergence of the minimizer of such a function under different hypotheses. The next version is an inertial method, which again involves the previous two iterates of the sequence. And again, under Lipschitz continuity of the gradient, one gets convergence, the minimizer of the function which was considered, which again is C1 and strongly quasi-convex. And another such method. So the first one was again to do Rani Piranfar. The second one due to my colleagues. And as you can see, there are several versions of such gradient methods for or involving strong quasi-convex Yuan functions. But the main idea or the main outcome is that they converge to the actual minimizer of such a function. And one has considered also dynamical systems involving such functions. Basically, there are two groups. One of them involving Iranian authors, Raimi Piranfar and his co-authors, Rani and Khatibzadeh, who have second and first order dynamical systems involving such functions. I didn't put them here. Basically, these dynamical systems do like they do in the convex case, their trajectories converge to the minimizer of a strongly quasi-convex function. And the second group involves my co-authors and Fan Tu Wong, and they obtain similar results under different hypotheses. So they had a bit of a different approach, different philosophy. And these two groups are, as far as I know, the the only ones which deal or which presented dynamical systems involving such functions. And from this, by scalarizations, one obtains again the gradient methods presented on the previous slides. And now we go back to non-differentiable strongly quasi-convex functions, which are involved in equilibrium problems. We consider an equilibrium problem, a quite general one. And the K here is taken to be linear subspace. It can be an affine subspace. If we want certain type of algorithms, it can be a whole space. It can be a closed convex set. And we have here a function, a bifunction, sorry, which is taken to be strongly quasi-convex in the second variable. Usually one takes it to be convex. And again, we extended the property to strong quasi-convexity. And also one can take it to be monotone or pseudo-monotone, which is what you see here. And some Lipschitz hypothesis needs to be fulfilled as well. These hypotheses show that or guarantee that we have exactly one solution to this equilibrium problem. S of K and F is the solution set. And it's a singleton as shown by Alfredo Yussem and Felipe a few years ago. And we have proposed a relaxed inertial proximal point method for solving such equilibrium problems, again with my co-authors last year. And you can see here many names. All these authors proposed a different method for solving equilibrium problems involving strongly quasi-convex functions. From the proximal method, the standard one, if you want, of Alfredo and Felipe. They also proposed a regularized algorithm. And then Vietnamese authors proposed extra gradient methods. African authors proposed the proximal method with extrapolation terms. And then a combination of these authors proposed two-step proximal point method and so on. So while in the case of an optimization problem, just minimize a strongly quasi-convex function. There are, let's say, two classes of algorithms, proximal and subgradient. In the case of equilibrium problems, as you can see here, the landscape of proposed methods is a bit wider and also involves people from different continents, again, Africa, South America, Asia, Europe. So all over the world, people are interested in equilibrium problems involving such functions. And again, probably one of the next steps would be to combine the ideas from the previous slide. So to propose probably dynamical systems for solving such equilibrium problems involving strongly quasi-convex functions. And for the last slide, I just put here some of the papers, of the recent papers, my work, of course, so that you see that I also contributed to these functions. And also the work of Felipe, where he extended the proximal method. First, he was the first one to introduce. He extended this method, the proximal method, to minimize such functions. Uh, as you can see here, there is a paper titled, like my talk, Strongly Quasi-Convex Functions, What I Know So Far, which was published in JOTA this year. And this is a survey containing the results I presented here and also others, because at some point one needs to make a selection. So basically, in this survey, we presented the state of the art of the research on such functions, or of the knowledge on such functions at the end of the previous year. And in the meantime, again, there were also new results, new dynamical systems, new algorithms. So the area is in development, even though it's not a central area, but still it's in development. And if I remember correctly, these functions are also connected to something called strongly quasar functions, which have a meaning in machine learning. So probably soon there will be new results or new applications of such functions in the area of machine learning, hopefully.